Hello, I just wrote my first paper on quantum computing, and now I'm going to talk about it. When I started to understand quantum computing, I noticed that the math and the circuits are not a perfect translation like in classical computing. For example, look at this equation of an exclusive OR gate. If we rearrange and simplify the Boolean equation, we can determine that an exclusive OR gate is made up of 3 logic gates like so. Quantum computers can't really do this so easily. They only seem to work when converting a circuit into a matrix, but not the other way around. My theory is that different quantum circuits can have the same matrix. Therefore, converting a matrix into a circuit would be impossible because the solution has more than one answer. This is pretty problematic if you can't tell. Math is the language of logic. It transcends our language of communication. It allows us to simplify complex concepts and makes designing practical. Suppose we had the greatest quantum algorithm ever invented, but we cannot harness it because it's stuck in matrix form. Let alone, does such a circuit even exist? We have no way of knowing. This problem is what inspired my research paper, and I will show you my solution to this problem. To solve this problem, I first came up with a simple way to turn an idea into a matrix. To do this, let's set up a simple black box problem. If we input a 0, the black box will output a 1. And if we input a 1, the black box will output a 0. What matrix satisfies this black box problem? To solve this, let's set up each equation as normal and use the matrix vector multiplication formula to find all 4 variables. Once we have solved all of the variables, we are left with a solved matrix. But now we're stuck in the same place as before. How can we convert this matrix into a circuit? And the answer is, I have no idea. Well, sorta. What we can do is test if a matrix can exist as a quantum circuit. I'll spare you the details on how this works, because it goes beyond what my paper is about. But basically, if you take a matrix and multiply it by its transpose, we should get an identity matrix when the matrix is unitary, which basically checks if the total probability was preserved, and still adds up to 100%. If the matrix isn't unitary, then the circuit does not exist. If we go back to the black box problem and test if the matrix is unitary, you will see the circuit does exist because we got an identity matrix from the unitary test. Okay, this is cool and all, but are there any examples of a circuit that does not exist? And the answer is yes. Take this black box problem for example. If we input a 0, the black box will output a 0. But if we input a qubit in equal superposition, the black box will output a 1. Basically asking the question, can we tell if a qubit is in superposition without measuring it? Measuring qubits will change the outcome and destroy the state of the qubit. This problem is what actually inspired my paper. So can this black box exist as a quantum circuit? No, it cannot. If we turn this black box problem into a matrix, and then test if the matrix is unitary, you will see that we do not get an identity matrix from the unitary test. Therefore, the black box cannot exist as a quantum circuit, and can just be ignored. Okay, so that's pretty cool. Are there any more examples? Yes, lots. So much in fact, that I was able to recognize a pattern. Here's my theory. Imagine 2 different sets of qubits. Let's call them set A and set B. Set A contains every possible quantum state with a spin of 0, and set B contains every possible quantum state with a spin of 1. Qubits from different sets can be compared, while qubits within the same set cannot. Now expand this concept by creating 2 different power sets that contain both sets A and B. Let's call these power sets families. Each family represents a level of superposition. For now, let's call them family 1 and family 2. The first family contains all of the quantum states that are not in superposition, and the second family contains all of the quantum states that are in equal superposition. Notice sets A and B are different in each family, but at their core, they are still the same sets. They just belong to different families and must be converted accordingly. Sets in different families cannot be compared, even if the states come from different sets. Only different sets within the same family can be compared. Okay, but how many families are there? Well, an infinite amount. Because qubits can be in many states at the same time, we have to consider a different family for every possible state of superposition. 50-50, 25-75, 40-60, 99.9 and 0.1. You get the idea. To test if all of these families actually exist, we can set up a black box problem where if we input a 0, we get an unknown output. And if we input a 1, we will get another unknown output. If we set up each equation and solve for each variable, we can use the unitary test to find all of the quantum states that can possibly exist. Notice, we now have 3 dependent equations to work with. If we solve for W in the second equation, we can now substitute W out of each equation, which just eliminates the second equation because it simplifies to 0 equals 0. Next, if we solve for Z in the first equation, we can now substitute Z out of each equation, which allows us to eliminate the first equation because it simplifies to 1 equals 1. Notice we are left with one equation left. If we simplify each equation, we are left with x squared plus y squared equals 1, which is just a continuous circle with a radius of 1, meaning any quantum state that touches this circle exists, which is basically all of them. Okay, this is fascinating and all, but are there any practical applications for this? And the answer is yes. One of the things I have done with my methods was create 2 new quantum gates. I call them the TSSE gate and the TOSE gate, which just stands for targeted same spin entanglement and targeted opposite spin entanglement. Basically, the TSSE gate will flip the target qubit if the control qubits are entangled in the same spin, and the TOSE gate will flip the target qubit if the control qubits are entangled in the opposite spin. After finding the matrix for each black box and testing if it's unitary, it wasn't hard to spot that the TSSE matrix was just C equals A exclusive NOR B, and the TOSE matrix was just C equals A exclusive OR B. It's up to your imagination on what you can do with these gates, but my point still stands. My methods can help create new quantum gates that progress the layers of abstraction needed in quantum computing. Another less practical but important thing to note is that it enhances our philosophical perspective on quantum algorithms. For example, here's a very famous quantum algorithm. It's called the Deutsch-Joja algorithm, quantum computing's first algorithm, which basically checks if 2 qubits are dependent or independent without measuring them. What matters about this algorithm is the circuit's structure. Notice those 2 Hadamard gates at the beginning and end of the algorithm. I found many other circuits that work exactly like the Deutsch-Joja algorithm. They may not be as efficient, but notice that they all have double Hadamard gates at the beginning and end. And that got me thinking, can black box problems in of itself be inside a family? Basically asking, can solutions only exist within the same family as the black box problem? And is it impossible to recreate the Deutsch-Joja algorithm without the double Hadamard gates because that solution would be in the wrong family? Just something to think about, I guess. And last, another useful application could be cryptography, the thing that everyone is talking about. In theory, we could use a bunch of quantum gates to scramble the data and then decrypt it using the same gates in reverse. However, the problem with this method is that it's basically a glorified Caesar cipher. A Caesar cipher basically uses a key to substitute each letter to encrypt the message. However, this method is very old, and modern computers can crack them very easily. And that's because we are only considering the sets, not the families. If we were to encrypt a message inside a specific family, now it's going to be much harder to crack, because we now have to consider what family the message was encrypted in. Like trying to tune a radio to a secret carrier frequency. You can't tell what message the family is in, because you can't compare sets from other families, and measuring the message would only give us an equally distributed wave function. And even if a spy tried every possible family to find the right one, we could just add another circuit to the system to scramble the message even further. I know this idea is new, and might be stupidly optimistic, but I hope this idea gets a proper trial. And last, before I finish this video, I would like to ask some questions. If this paper were to have any significance, I would like to give my followers some sort of compass to help steer the research. My first question is a bit ironic, but how can we actually convert a matrix into a circuit? Since I hypothesized this conversion to be impossible, maybe we can use AI. I know you're probably rolling your eyes with the amount of hype AI has recently generated, but artificial intelligence is generally very good at pattern recognition. And I think we can possibly train a neural network to spot the key patterns between matrices and circuits. My second question is, are there more sets in families? Because quantum states are complex, it's not uncommon for a quantum state to have imaginary components. And I wonder if a qubit with an imaginary component belongs in a unique set or family. I haven't really checked for myself, because honestly, I'm just too tired and unmotivated to do the research myself. So please check that out if you're interested. And my last and final question is, what did you think of my paper? Please leave a comment below. I don't really expect my paper to be much of anything, but I would really like to hear your opinions and theories on the topic. As always, thanks for watching my video, and for giving my paper a chance. Peace.